Hello and welcome to a new session of Hitchhiker's Guide to the Glamorous World. And today I'm joined here by Konrad Hinsen. Hello, Konrad.
Yes, hello, Tudor.
So Konrad has an interesting project. He's building an interesting project called Leibniz on top of Glamorous Toolkit. And the whole session today is going to be about him giving us a tour of that project. So the scene is yours, Konrad.
Okay, thanks for this introduction. Well, I think I should start by sharing my screen to show things and share screen, desktop. And now, do you see my screen?
Yes, yes.
Nice
We see Glamorous Toolkit.
Screen. Okay, yeah, so that's the screen I'm looking at for large parts of my workday over the last few months. Well, I guess most people watching this will have seen other screens of Glamorous Toolkit before, so don't have to go into all these details. The top row is my personal extensions. So there are 5 of them, but they are not the topic of today. These are very small tools that I use for organizing my daily life. What I want to talk about today is this piece here, which is added by my Leibniz project. And well, this is the entry point is a Leibniz database. So for those who haven't looked at this much before, Leibniz is basically a system of database. A Leibniz database is basically a kind of wiki with where each page is a list of snippets of various types. It can be text, it can be code. So this is basically a wiki of computational notebooks, to put it into terms that are familiar from other technology. And what I've been doing over time is I've been trying to add a new kind of notation or language inside this Leibniz database. So I call this a digital scientific notation, and maybe I should say a bit what I mean by that. I made up the term, so there's no point in looking it up on Wikipedia. I picked this term to make a distinction with programming languages, because what I've seen happening, I mean, my background is computational science, computational biophysics, most of all. And what I've seen happening over the last 30 years that I've been doing computational science is that whereas in the beginning, people used software to create tools based on well-established scientific models. Something like you have a differential equation and you write a software tool that solves it using some approximations. We have moved to a world where more and more of science is actually immediately done in software. If you look at something like the big climate models, for example, they are basically Fortran code. So this scientific model is a piece of software. And these pieces of software have been growing and growing, like all software, and getting more and more complex. And some of them have been abandoned by their authors because they don't understand how they work anymore. This is not really a nice development, I think, especially we have at the same time a movement called open science, which is getting a lot of support recently, which wants scientific research to be more transparent, more accessible, not only to experts, but only to policymakers, decision makers, the general population. So the idea is to create more trust in science by getting more people implied with how the decisions are made and how the process is organized. And if the core models that people work on are millions of lines of Fortran source code, I mean, there's a natural limit to how transparent things can be, because even somebody highly trained in the matter doesn't really understand all the aspects of the science behind it. So yeah, that was the kind of my motivation for trying to do things differently. And so what I'm trying to do here is to move away from a world of scientific computing done by tools that encapsulate the science, is to move to an old idea, which is a computational medium. A computational medium is a substrate where you write things, where you can write in the sense of text or pictures or whatever else, to record and communicate and collaborate on the science, and have the tools organized around this medium. And the medium remains at all points accessible to human readers. So this is my attempt at implementing this idea. So my computational medium is Leibniz, which is a part of Glamorous Toolkit. And I mean, I would never have attempted to do this implementation without all the prior work which is in Glamorous Toolkit. I mean, I'm not aware of any other wiki of computational notebooks where I can actually plug in my own computational language. So that was a nice experience. So yeah, so that was the general motivation. So while you can read it up if you everybody can download this and read through this if they want to. As I said, some important things for me is that Leibniz is not a programming language. So the point is not to write programs that do things. And in fact, you can't. There's no way you can do something. This is a purely declarative language. There's no way to print or there's no output. You can only evaluate things, but there's no way to have an effect on the outside world. So that's it's not a programming language. It is also not a computer algebra system. Well, this is something. This is probably I won't go into right now because people won't get this wrong idea before having seen the rest. Okay, so I think I'll start by showing what the typical page would look like. So I'm not yet at the point of really defining scientific models of any reasonable scale for real research. But this is an example page I made to just explain a simple algorithm, which is about 2,000 years old. It's an approximative method for computing square roots. People familiar with numerical methods may better know Newton's method for finding roots of equations. This is a special case for doing square roots. But then, yeah, this is really very simple algorithm. So that's the point is to have a simple example. So when you look at this text, this is an explanation of an algorithm, and everything which is blue in there is code in my Leibniz language. So it is completely embedded. It is implemented as Leibniz annotations. So when you put your cursor on this, you will see this is what I actually type. And when I put the cursor away from it, it is rendered visually in a slightly different form, where some things are italics and some things are underlined, and some things are low contrast to enhance visibility. But behind all that, there's a text version that I actually typed in. So all these elements define my algorithms, my context, and I can always click on this and get an inspect review on that, which for this one is not terribly interesting. It didn't pick it just looks at this. This will become more interesting. I try to add more and more inspect reviews to these various objects, and well, people who have looked at Glamorous Toolkit before know what inspect reviews are and how important they are. So I expect to have additional ones where I can actually play with the code and enter expressions, evaluate them, and so they don't exist yet. This is all for the future. So one of the basic idea is that these blue things, which define the formal parts of my page, are I'd say they are small pieces that integrate into the narrative, and their order is completely arbitrary. So there's no constraint on how and where you put things. I can reorganize my text, unlike a programming language where you have to declare a variable before you can use it, define a function before you can call it. There's no such restriction at all in Leibniz. You can very well say, I defined something. I will later define this thing and then continue to talk about it without ever defining what it means. So that's one reason why things are short and small. So they are supposed to fit like mathematical equations. Inspiration, it should look and feel like mathematical notation, but it's behind that you have a formal language which is well defined. You can use programs to work on it, and so on and so on. So let's try and look at something else. This is a rule. So Leibniz is based on term rewriting. For those who have, so as advanced computational science users, they may know computer algebra systems, which are also based on term rewriting. So this is familiar to at least some part of the scientific community. And yeah, it has the advantage of allowing this approach of tearing things apart and formulating everything in very small pieces of code, which can be formulated inside the page. So what in a normal programming language would be a function is in a term rewriting system a read-write rule. So here's one of them. Yeah, so maybe I should still first go slightly through this algorithm nevertheless. So what you do is you write, this looks like a function call, right? You say here on of 3 arguments, x is the number for which you want to compute the square root, epsilon is the precision to which you want to compute. It's an iterative approximative method. It stops when it gets close enough. And e is an initial estimate. You have to start from some point and then it converges to the square root. And behind the columns here, you see something like a type specification. So the x is a non-negative real number. This double stroke r is the mathematical symbol for the set of real numbers. And I have a subset here, which is a subset of non-negative real numbers, because square roots are defined only for non-negative real numbers. The precision is a positive real number. So this one may be 0. The other one may not be 0. It's strictly positive. And the initial estimate is a non-negative real number as well. And the result, being a square root, is a non-negative real number as well. So at this point, I've only said what this is. I've absolutely not said how to compute it. If I can compute it, I've just say I define something like a function called here, and this has this characteristics, and then I can continue to talk about it. So here, actually, I do provide immediate implementation, which consists of 2 rules. So this is the first rule, which says these are the underlined things are variables. And the variable declarations are in lighter font so that you can immediately see where the real rule actually starts. It's for readability. So for every non-negative real number x and any positive real number epsilon and any non-negative real number epsilon e, the rule says that that this will be replaced by on the right-hand side. Well, I don't know. This for me, this is behind. I have to move the small videos below. Okay, so this is replaced if this is a condition. If the absolute value of x minus e squared, e is the initial estimate, right? So my current estimate, I compare the square of the current estimate to my value x, and if this is already smaller than my criterion epsilon, then I stop. Then my current estimate actually is the result. This is the end criterion for the iteration. And the second rule is this one, which is the more interesting stuff that does the real work. So which is only called if the first one fails. So that's why it has a number. It is called number 2 here on number 2. The other one is here on number 1. So the order is doesn't follow the order in the text, but the numbering. It says, well, if the first one is also apply, if I'm not yet done, then I have to do one more step. And this one more step says, I have to make this bigger, otherwise I can't see it. It says that I replace my current values. I keep the x, of course. This is my input value. I keep the epsilon, but I replace my current estimate by 1/2 times the sum of the current estimate and x divided by the current estimate. So I replace my current estimate by the average between itself and the inverse x. This shows another nice feature of Leibniz. This is underlined in red. And underlined in red means that Leibniz cannot promise that this is a valid term, because division is not defined if you divide by 0. Now I'm actually thinking about it. Why does it epsilon? Now, okay, exactly. E is
non-negative.
It's non-negative, but it could be 0.
Yeah.
So, which is actually not reasonable, because it is reasonable. If you want to do the square root of 0, you can start with 0. Okay. So underlined means that it might be a valid expression, but it's not guaranteed to be. Everything else which is not underlined is guaranteed to be valid within the types that I've given. So this is not it's not forbidden to write this. It's just underlined. So it's a warning sign. And well, if it works out, it's fine for everybody. Yeah, then we have you can look at an example. So you write down here an expression. Well, I can't compute. I said everything I said it's real numbers. You can't compute with real numbers. Everyone who has looked a bit at numerical computing. It's one of the basic problems for numerical computing that the real numbers are too large, a set too large to be represented in in finite terms. So you cannot compute with real numbers. So what programming languages don't provide them, and sometimes they use the label real for floating point numbers, which is something very, very different. In Leibniz, real number is a real number. You can talk about real numbers, even if you can write them down. But when you do a concrete computation, well, I have to use something that I can compute with, and I use rational numbers, fractions. So here, this is 0.1 written as 1/10. And here in my hidden code, I want Leibniz to show me what is called the normal form. In the term rewriting vocabulary, the normal form is the fully evaluated after the application of all rewrite rules. When you can no more simplify or rewrite the term, this is what is called the normal form. So this is the result, which is, I'll also look at it here. It's 17/12. I trust it. And this is, again, the sort, the Q is rational numbers. And this is a positive rational number. What is more interesting than computing this for a number is to look how this converges if you get if you reduce the precision, increase the precision to reduce the error allowed tolerated error term. And so I define another function, which is called the error function. Well, this is another feature I've invented. Okay, I didn't say what I call a context. The context is everything that defines what is a valid term. So it's a list of, that's something that says that you're allowed to use real numbers, you're allowed to use integers, you're allowed to use a thing called hieron, and so on, so on, and so on. And this is what you would typically extract. If you want to, suppose you want into some fancy scientific procedure, you need Hieron's algorithm. It's unlikely, but you would extract all those terms in blue here from this page and work on that. But you don't want the example terms, right? They are there for illustration. They are outside of this. So this is the subcontext for talking about convergence. So if you ask for the code, the specification of the algorithm, you don't get the example code. It's kept apart, and that's why it's shown in magenta, not in blue. So okay, that's another function, and then you can it's defined here. It's the absolute value of the difference of what I want and what I ask for, and then you can do
just a question.
Yes.
So that one, the expression there, Heron error.
Yeah.
That looks like a function, but it isn't. It's not. Doesn't look like blue.
Yeah, but it actually would be blue if it weren't in the special context for convergence discussion. So it's not part of what is in the page what you get, but it is actually. Otherwise, if I put it into the main context, it's blue.
And how do you do that? Or how would you do that?
I would.
It's in the description.
Remove the subcontext.
Subcontext convergence. I see. I got it.
I have to do it for both. So now it gets blue.
Yeah, I understood.
And this one would get blue as well. It should still work because it's now in the main context. So now that should. Maybe I made a mistake in typing this. Sometimes itself. I still have a problem with updating the code. That's something I'll go to the hard way of I reset my cache. That's the hard way of making sure the next time this is computed, I will actually get it to process the new version. Now it has to go through all the page again and then do everything again.
Interesting.
There's still something I've been doing recently, figuring out how to propagate changes in the snippets to. No, there's still a mistake.
Okay, that's not a problem. We can undo. And
yeah, I can't undo now. Is there an undo in these function pages? I don't know. I can type it again.
Yeah, I think undo should work because you didn't leave it.
Yeah, but what is that an undo function? What is that? Control Z?
Command, yeah, Control Z.
Yeah, sure. Oh, yeah, I have it back there. I never used undo in this page. Well, I have to get used to that one. But no, I can do it by hand. It's not so complicated. So yeah, so this is then my rule for computing my error, and then my really latest addition is to actually put plots into there. No, my plotting code is very basic, but well, anyway, this is, it says XY. I still have no access labels. This is really the convergence parameter epsilon here. And when you decrease it, you get it in kind of steps. It goes down at some point when you add an iteration to it. And here, this is the smallest value is here in the end. And I should be able. So actually, the plot is a term. So it's a special term. So this is, it shows the plot, but it's a normal term. So I can actually look at the numbers. So I have this one. It has a normal form.
So this is the tree that makes the tree that makes the.
It's the terms, yeah. The tree is. This is the term. So you can see this is the outer operator is line plot, and then it has argument here and error, which is here. First argument 2 here, and then you have this array here, which is the values, which is the values of the error cutoff parameter that I used for my plot. And then if I go to the normal form, it shows it actually does the computation. So the functions apply to a whole array, and here I can see what it actually comes down to. So the values that are plotted are actually this is the x and the y values. So you get the data and the plots in the same term in this way.
Nice.
So this is a special subclass plot term that has one view more. So all these are standard inspector views for terms, and if it's a plot term which has a special tricky hierarchy to guide it to use a special Pharo class that lets me add the plotting code. So that's how I got the plots. So this needs to be very much improved. But well, yeah, this is boring programming work. So it's that's something I try not to do too much.
With side effects.
Exactly. Yeah, exactly. But when I think this is very important to have this possibility. I mean, you can't really do explanations of science without plots. So this is. It was very important for me to at least show that it can be done in principle, even if my implementation is very basic. So this is like other Lepeter things. You can open and close the representation. I think this is a very nice feature now. So you can glance over the text rapidly, and if you want to look at the numbers, you can have them, and then you can click on it to get the details. And I think this way of working, which of course everybody who knows Glamorous Toolkit is familiar with. I mean, this is very well adapted to this kind of working. So it's where other people work in coded on Pharo code, while I work in Lepeter pages with my own code. But the way of working is very much the same. And yeah, it's addictive. So. Yeah, that's for the Glamorous Toolkit people here. That's you can change the page view to an inspector view, and then you can actually. That allows me to put buttons on there. So this is my debugging page, my debugging view. This is just all the blue stuff.
That's so exciting.
So this is if I ever get lost in these things, I can say, okay, I don't need the text anymore. I just want a clean view on the code parts. So here I see all the types of each annotation which are hidden here because they're not important in the context of reading the stuff, but they are important for understanding this. So yeah, this is really just parsing the blue stuff and putting it separately.
Yeah. And in the context used,
this is dependent. It's a kind of dependency checking. So this is what I make use of other pages. The page called plotting, the page called absolute value, the page called read numbers, and the page called functions. I have subcontexts in my view, which is the one called convergence. So all this is not easy to see from the page, but it's very easy to see from the debugging page.
Yeah. What happens if you go into one of these in the subcontext? Yeah. This is anything.
Well, this will get me to the page that's the divided.
This is exciting. Yeah.
So, but this is just the. Actually, no. Here I actually get into the annotations.
Into the two. Yeah, exactly.
This is really the Pharo objects produced by the parser.
Yeah.
This is a debugging view. It's not really meant to be used by people in the end. What is meant to be used by people for doing computations is the computational context view. Let me get this one. This is the first button here. I get it. Okay. this button, this is really meant to be used by end users in a certain sense. So this gives you the view of various views on everything you have actually defined, on data structures you have ended up defining by these declarations. So I mentioned the kind of these type annotations. Well, people in ternary writing don't call these types; they call them sorts, and I've stuck to that jargon for familiarity. So this is the sort graph. So there is a sort called B double stroke B for Boolean. So this is used here for the conditions, for example. There are Booleans. And this is the number hierarchy. It's fancy. So it has real at the top, and these are subsets, subsorts, which represent subsets. So the non-zero real numbers are a subset of the real numbers, and the rational numbers are a subset of the real numbers, and so on, and so on, and so on. And down there you have natural numbers. You have zero, the set of zero. There's nothing at zero, and the non-zero natural numbers. So you can put this together. That's all I have in this one. Then I have defined what is called operators. That's what make up the terms. And these are all the operators that I have in my collection now, directly from my page here, or indirectly because I've used real numbers and absolute value. So here I have subtraction. Now this is negation, exponentiation, addition. And for example, addition is a pretty messy one because there are many ways to add things. So you can have a look at these.
This is so cool.
So these are the various declarations for addition I have. So that says that the sum of two real numbers is a real number, but if the numbers happen to be natural numbers, the sum is a natural number. And the sum of a natural number plus a non-zero natural number is a non-zero natural number. So there are many specific cases that have the advantage that you can, without actually doing the computation, already say something about what you will get. You can also get a graph view on that. That's even nicer for small ones. If it's too big, it becomes messy. So this is how these various additions are related to each other. And this was actually one of the most important, because if you get something wrong, and I mean initially I got a lot of things wrong, and this thing breaks down. So the slightest mistake will completely mess up this graph. So this was my main debugging tool for quite a while. I defined something. Hey, let's look at the operator hierarchy graph. It is still makes sense. That was my first quick check. So I actually spent I think something like 2 days to get this graph really nice and usable, and this has saved me a lot of time in the end. So this is really an important debugging tool. Very much appreciated to have this possibility, and that's why I'm a fan of Glamorous Toolkit. Anything? Well, the others are not more interesting, I think. I don't have really any strange cases here. I get, well, these are simple cases. They've only a single operator. There was no point in doing a graph. But yeah, the number of ranks is given here. So yeah, division is interesting maybe because it has so there's no division between real numbers. You can the most general one is division of a real number by a non-zero real number. So if you divide by 0, this is simply not a valid one. And then that's another. Now we're getting into the messy details, but this is actually quite important of my kind of type or sort system, which I didn't invent. I mean, I've actually all the ideas behind this I've actually borrowed from a specification language called Mod. I have no idea if this is widely known or not, but it's the latest part in a line of development that goes back to the 1970s on algebraic specification languages, and basically Leibniz is a very different syntax for a subset of Mod. But the very different syntax matters for me. Yeah, so that's it. What you get is here the square brackets. So you have all these sort graphs. It comes in sections. So there are arrows between all these number types, but there's no arrow between the Boolean type and the number types. So that's what makes them separate kinds. A kind is a connected component in the graph, basically. And the type checking works on 2 levels. The strict version is at the sort level. It has to fit. But then there's some allowance for matching on the kind level. And then you get the red underline. These are terms that could potentially become true become valid by rewrite, so we accept them as intermediate values. And they basically serve as some kind of error label. So if you divide by 0, let me see, I can do that. I just go to the real number context. I think I have so this is how real numbers are defined in Leibniz. It's a text, it's a Lapita page like everything else. There's some very little Pharo code in there. There is some Pharo code in there, but very little. And I think I have at the division example. No, it's not in the real number case, it's in the rational number page. Rational numbers. This is rational numbers.
How do you define the uses part? That definition of the uses, how is that?
It's another annotation.
I see. Yeah.
And then you just link the right thing to be opened there. Yeah. So it's not this is a page reference, a Lapita page reference.
Yes, yes.
And they are not the same because I can refer to a page for comparing, for example, but real numbers don't use floating point numbers. They just point to them because they are different. So they're not the same color, by the way.
Yes, yes. Noticed.
It's a bit subtle, this color stuff. Huh?
Very exciting.
So yeah, you can do very nice stuff in here. I spent some time optimizing this display here, but I like it as it is now with various levels of contrast and underlines and so on. So the idea is that the most important part stands out, but the other stuff doesn't get eliminated.
It's very, very interesting.
I think I have a division by 0 in here just to show how it works. So there's Pharo code here. So there's some example. For example, the numbers are multiplied in Pharo code. So when you do a multiplication of two rational numbers, it executes this. So these two are measure methods that ensure that these are actual literal numbers. And if that's the case, it just does x times y. And if this fails, it raises an exception and the whole rule is simply abandoned. So there's some behind the scenes stuff, but you can basically write Pharo code in there, which is quite nice.
Well, what would be interesting would be to see in that expression highlighted as Pharo code. The x insured number, y insured number.
Oh yeah, it would be nice to be able to click on this and actually do a search for. Well, I don't have this for now. I just do this. We have we have spotters. But you actually nice. You get to see where it happens in those pages.
Yeah.
But if you want to see how it is actually implemented, this is this one. So this is plain good old Glamorous Toolkit stuff, which you know better than me. So voilà. This is what it looks like. Basically, for general term, it says failure.
Yeah.
And that means the rewriting abandons it. It basically
doesn't go inside.
Yeah, it takes this rule to be non-existent and goes on with the rest.
Very interesting.
Oh yeah, here, that's what I want to show. The division by 0. So
it's red.
It's underlined in red, saying that there's something wrong with that. You're allowed to write that. If I do something completely forbidden, like divide by a character chain, then it will actually not even pass. It will even say this. I can't do that. So you never get. You will be stuck at the level of this annotation, and you'll never get a proper. You get an error message behind it. But here it says something. Well, doesn't have a sort. It doesn't have a valid. I don't know what this is, but it is of the same kind as a rational number. So this is what this square bracket thing means. So that means it is something in this space, but nothing well defined. So I could now have a rewrite rule that defines what 1 divided by 0 is, and that would make it a legal term. Well, there isn't, of course, but I could say, okay, for my current purposes, 1 divided by 0 should be taken to be 1. I can add this in a later part of the code, and then it becomes valid retroactively.
Super exciting.
So again, all again, these views are very important. I would have been lost without them, completely lost.
So can we go back to that expression, the evaluate number term, the one with the Pharo code inside? If you click on that, and if you click on the expression to inspect it.
Oh yeah, that's a good point. What does it give me? Hey. Okay, it's just slow. It's Zoom in the background taking up my computational power. But So this says it's a function rule. Well, that basically means a rewrite rule defined in Pharo code. I don't think I can really dive into that for now. The problem is this Pharo code doesn't exist anywhere else than in the string. So what happens is the object actually contains it compiled as a block. Here it is. And that's something I can. This will come. It's just my computer being slow. So this is just it has been compiled into a block closure, and they can look at it and work with it as a standard Pharo object. And here you see now I can actually use all the coder stuff.
I think it's not enabled in this view.
But
okay. Yes.
Okay, but that's I didn't even think about it. You can dive down into it. You just have to go through the raw view. So I always feel when I click on the raw view that I missed something, that I've forgotten something. But then I'm always happy it's there, of course.
Yes, very interesting. But isn't this so? I was thinking about your syntax, right, in the function rule. Isn't there a way to if you look into the syntax view? Isn't there? I mean, because you have these parts, and you're even highlighting them differently, and there would be a way. There should be a way to go to one of them, right? So if I click on one,
I mean, again, for now it's the raw view. I can look at separate the pattern that is being matched on the left hand side is a standard Leibniz.
Yes, exactly.
And again, the right hand side is this block. So it's I can also have the code as a text string. So it's all there. I just don't have the views that let me dive into that. It's not yet done, but it's all accessible.
Another way would be
it's the left hand side is Leibniz and the right hand side is Pharo, basically.
So the one thing, because what is interesting again here, like I'm looking at it from the platform perspective.
Sure.
So first of all, I think it's I think it's super exciting that, like, when we're creating GT, we're just thinking what are the points that are hard-coded, and we want to get rid of those. And the idea is to get rid of those hard-coded points is to basically enable people to create things that we cannot imagine. This is one of those things which we definitely did not create GT to enable what you've done, right? And so we're looking at just what are the pieces that we could use to put things together. But you have here a couple of very, very exciting. First of all, it's amazing for me that you've managed to do this pretty much by yourself. Like there was essentially no question asked. Really?
No, I don't quite agree. If you check,
but I mean, not about
I did ask questions.
But not about I mean, there were questions which are very superficial related to
technicalities
to this, right? So it's just like little things, not a core thing. How would I architect this, right? And
no, that was pretty obvious, in fact.
Well,
actually, I've been working on this for a while. I was waiting for the one thing. I remember very well. I said, I hope they will, before long, they will actually allow me to write my own annotations into Leibniz pages, because I really did that. And I had worked on the project before, so that was really a liberating step when I got this one, the parser extension, because I knew this was essential to actually get to this point.
So, and exactly, so those kinds of like when we are thinking, right, we don't know what we're what people want to do or could do with this, and this is super informative for us, right? And then there are these other things where, right, so here, for example, you have one single rendering, but our goal is to be able to, so that, for example, you get completion inside your strings when you're writing your Pharo code, and all mechanisms should be in place. So actually it would be interesting for us to work with you.
So basically, when the parser detects that I have Pharo : then afterwards it could basically make this a piece of coder with all the support for Pharo code. I agree, that should be possible. Yeah.
Right, and with syntax highlighting should just highlight that part differently, and so you can write.
I agree. That would be nice. Yeah. I would like to do a complete. I know it's possible. I've seen Sean Denigris doing this. Implementing completion in annotations, but I simply didn't get around to that yet for now. So
right, so that should not be.
I really like to get completion in here when I type LZ rule : I really want completion of exactly the operators in my context and so on. I know this is doable. It's just
so what we've done it so that you can, like, you will get completion. So sometimes there are a few examples. So for example, if you look into if you open a page and then you do GT method as an annotation.
Yeah. That's what I'm saying. I'll go to my Scratchpad page and
so let's just add.
It's just GT page I haven't really used.
No, GT page, GT method.
GT method. Yeah, that one is a classic. Yeah,
okay.
that has.
So now, okay, so now say object, for example.
Object. Oh.
Capital.
Oh, okay. The object class. Okay.
The object. You have to give it a name.
Unfortunately, object. And now it should show me the methods of object, right?
If you do higher than, right? So.
Yeah.
And you could do control space, but here there seems to be, I think your test plot might be too expensive to do.
Oh, I don't need this anymore. This was for testing plots. Okay. So yeah, that might be a small. Okay, I'll retry.
And you can now put the curly brace at the end. It's easier. Control space should give you. No.
What did I get wrong there? Yeah.
Something is.
I hope I'm in a text a bit. Yeah. No, I've done this. I'll start again. So GT, because even there I should get completed first. Exactly, method, right. And now I get.
Okay, now I can do.
Yeah, actually, it's that I have to get. Yeah, it's here. I have to tie objects. That was wrong.
Right. Now but you don't have to object. You can directly type object there, but it's fine. Okay. And now, if you do higher than, right? Now this will give you the completion of the methods that only exist in object.
Yeah, for now it gives me the completion for something else. Oh no. Yeah, sure. That's it. Yeah. Well, of course, object has so many methods that
yes. So if you do, for example, proto object, then you will get a much smaller.
Yeah, that's a smaller one. Yeah. Exactly. And now I can.
You need higher than.
Yeah.
And you have
right. So forget that one. Yeah. Yeah.
So what this means here is that here we have a completion that is, so first of all, GT method is an annotation, which is a custom one. Then you have the completion of the arguments, so name and so on. Then inside one of the argument, you have the first completion of the class. And then afterwards, you have, depending on which class, you have the completion of the terms inside of it, right? So this is one of that example where you can, it's reasonably, it covers pretty much everything.
Sure. There's several levels of,
several levels of nesting.
I'll look at that one, yeah.
And so that's,
yeah, I guess it basically comes down to providing the list. Well, my job was mainly to compile the list of things that are valid there, because that depends on what I'm doing. So here it's method names. So at some point this time here it's an introspection of the class to show all the methods that go with it, and I'd have to do this for myself for my own code. Yeah, sure.
So that's
really nice.
Then the other thing is about the computation. So I noticed that it can be the computation can be extensive.
Yes.
And so one thing that you could consider is the support for parallel images that we have, so that you can delegate the computation to a different Pharo runtime.
And that the point would be that since I have 4 cores, I would run it on a second core, right?
Yeah.
Yeah.
You can even delegate multiple, right? So you can have a pool of this.
I never looked into this. What is the good entry point for that? A good entry point is something we call remote runner. Remote. G2 remote runner. There we have it. Oh, there are examples. Nice. So, well, actually, usually I start with references. It's the easiest way to see how people use it.
Yes, but it's still not entirely. It's not yet really made very public, but because we're still very much working on it. But we basically we now have cases where we work with 1,000 processors, for example, using this and delegate work. And so essentially you have a whole distributed system that is also working asynchronously and works not based on push, but based on pull. So you can spawn workers and then they can distribute jobs. So if you can take your computation and split it into little pieces that you can give to different workers, you already have pretty much all the infrastructure that is needed to do this the distributed computation.
Okay, so what is sent around there? The communication is what do you send between them, the images?
Proxy objects. So it virtually works with, we have a proxy object model. You can even actually inspect things on the remote image.
Okay, so you actually don't even have the data on the main image.
On the main image, you might or might not. So it's up to you. It depends, right? But you don't have to have it on the main image. You can just have it on the workers. Yes.
Okay. No, I'm wondering because I mean, my data structures can become pretty big, and if communication becomes more expensive in computation, then
yeah, of course. I'm simply saying that. So there is also the other thing to keep in mind is that we also have the possibility of these worker images to be in sync code-wise with the main image. So, so for example, a typical case here is to run examples or tests in another image while you're working. So you work, and then at some point, like the other image, the worker image is kept in sync with your with the main image. So the code changes are there, and you just say run the tests, and they don't block your image. You can just continue doing.
Yeah, that's nice. But I guess it's image. My code is mostly not in the image. It's in a limited database. So
yes, so it is imaginable, right, to have that one also do a similar thing. But basically, it doesn't have to be a short-term thing, but it's probably something that you might want to
definitely
consider, right? And so the basis is the platform exists. And we are actually
I'll show
using
you why I think this is important for something different, because one of the things I'm playing with is to use Leibniz for writing scientific workflows. Why do I have this? I didn't get very far with that yet, but no, the idea is that now I should maybe go for the example rather than this boring definition page. I'm working on a course on scientific workflows, and at some point I looked at these horrible make files. That this is not how people should do workflows. So I said I'll try to do it better. So my idea is here to have Leibniz code, which basically successively compiles down to Python scripts which get executed, and those I would definitely prefer to run somewhere else, and probably even some level above. So if the remote image can run Python, then I see no reason why it shouldn't be able to if it's configured correctly.
It's a normal GT image.
Yeah, exactly. It's well, except that it has no user interface, I guess. But, yeah.
it doesn't have a user interface, but you have remote inspectors. That's the other thing.
Yeah, of course. Nice.
So
I have to look at that at some point. It's not my current priority, certainly, but especially for here. This first, well, I have really a few lines of my workflow, but if I actually get this to work, then it will happily occupy 100 processors for a few hours. So
yeah.
And then of course I have to have them, but that's another question. So I have to move away from my laptop, I guess. Can I do remote images over the network, or does it have to be in the same memory space?
No. So we, for example, we're doing it. We have we're working with the cluster on AWS. Well, actually multiple. Good. And you can control them from your local image. So from your local
you basically have your dashboard, and you can. This is exactly what I want to do. Nice.
Yeah. So this is what I'm saying is that there's the infrastructure underneath is being built. Is not entirely visible yet, but it exists and it's there, and it's we're using it.
Yeah, I've seen discussions so crazy about these promises and so stuff, and kind of filed this away for. I have to look at this one day, but.
So the promises and the futures, right? That's we needed it both on the UI perspective.
Yeah.
But it's also was like just the platform for executing. Basically, it's a distributed Smalltalk. Is one, and then we have the asynchronous and the promises support. And then when you combine them together, then you can build user interfaces that don't have to wait, for example, for things that happen. So for example, here, right, I can see that your previews, right, are using asynchronous, the previews are being generated asynchronously, but you're still using just one processor. So that's why the UI might get a little slow while the rendering happens. But you can imagine the same computation, and you're only sending back from your worker image, you're only sending the rendering string. You're not sending the whole data back. Yeah. So the main image does not have to have anything about your model, and that can live with this image. So
like in the good old days with X windows and remote window and so on, yeah. Except at a different level. A level I can I would want to work, and I don't want to work at the X windows level, of course. That's nice.
Yes.
That reminds me of something else I found. I noticed, this updating stuff. Something I noticed is if I use if I have a page link in Leibniz and I edit it, it actually updates the references everywhere else.
Yes.
So that's something also. So that actually means there is a way to tell a page that a page view that it has to update itself because somebody has changed the model underneath, right?
Yes.
Is this just some announcement I have to figure out and send, or?
Yes, right. You're saying, for example, if you're going to rename one of the pages that you're using, that you want to go and update all the usages of that rename, right? Yeah. So here it might be that. So obviously for links, well, links have direct support. It could be that maybe your uses clauses should create explicit links.
I would like to do that, in fact, except that I don't know, and it wasn't my priority.
Sure. So if you're looking for, let's see,
probably look at the GT page thing, right? It's the
if you look at if you look at LeLink, search for LeLink. Yeah. Did you look in the class hierarchy? If you look on the class hierarchy side.
Okay. Right. So attached text. I would make my own then, I guess.
Right. So the whole idea here is to have to be able to have typed links, basically. Between and you can have yours, and then through those we can probably manage the dependencies better, and then
That
propagate
looks good.
things.
I think I'll look into that. That looks good. Yeah. Yeah, of course, my use things, these are links, of course, but links with a different meaning. So that's exactly what I need, another kind of link. Yeah.
Yeah. So,
excellent.
And also, like, these links, right, they are stored separately. So you have basically a place where you store pages, and then you have another completely separate place where you store links, which means that also that you can have links that are not visible in text, for example. So links are external things.
That's somewhere. No, I have to get a view on the database. This is not the database.
Yeah, for example, incoming links. If you go there.
This one. No, I say.
You didn't.
Nice. I actually have dependency graphs on my pages.
So if I have a uses thing.
Yeah, exactly. This is my personal link management, which is completely independent, which it should not be, but for now that's what it is. And, but it's quite useful already. So
nice.
Now to get a view on the database, I would probably have to go to the raw view first, right?
You can, or you can just open a snippet and say, okay, let's say self database. Yeah.
Yeah, sure.
You see that.
Yeah, explicit links. Yeah, that's what I vaguely remembered. Yes. There was a view of links. Yeah. Okay. So, yeah, they have the link type. Okay. That looks interesting. I think I will spend some time looking at these things.
And so like it can be that this is maybe not entirely as useful as it should be, but you have such a remote your use case is so remote from what we are typically seeing that it's a very interesting. No, but what I'm saying is it's very interesting. It would be a very interesting way to exercise the model basically through your requirements. Definitely.
Yeah, I'll play with that, and I will complain if things don't work as I think they should. But I mean, I was really impressed myself that at some point I said, I don't know how far I can go. I'll just go for it. I mean, it's a prototype, and we'll see what happens. But I didn't quite expect initially to be able to put everything into Leibniz annotations. Basically, I know they weren't made for that. I'm fully aware of that. So.
Well, it's not that we didn't make them for that. It's just that we didn't exercise them for that, or it's not necessarily entirely obvious that it's usable.
No, exactly. I agree. So I was surprised how well it works. But I mean, I have certainly some user interface issues with latency when computations are a bit lengthy. And of course, all my rewriting code is anything but optimized for now. So it is pretty slow. So of course that's a bit of the risk. Of course, now you tell me I can offload this to other processors, so I may never optimize them and just throw more processors at them. So it's not good for the environment.
Well, so for me, it's how long did it take, like, to build this?
It's never been my main project or only project. So I've been doing this as a side project for quite a while, and so I've started working on this whole project in the Pharo. No, the whole project goes back to 2016 or so. I started the Pharo version. It was my first serious thing when I started discovering Pharo, which was in late 2018. So and I first did the basics in terms of data structures in the rewriting engine and so on. So I didn't even use any user interface at the time. When did I start to use? Yeah. Well, I mean, the rapid integration is recent because I waited for the extensible annotations, and it's not that old. That's maybe less than a year, I think.
Yeah.
This really latest part, and at some point I was quite annoyed because I had to use petit parser first, and I had to do everything in SMAC again. I was quite annoyed by this. And then you had to do the parser. In the end, of course, your second parser is always more efficient than the first one, no matter what it is. So actually redoing it was actually beneficial. And was the occasion to improve the syntax and all these kind of things. And this isn't very old, all the stuff. So it's a couple of months. So the Leibniz integration is very recent, but the computational engine behind it, I've been working on this for quite a while, yeah.
But it's still, I still think it's quite impressive, the level at which you could bring everything together. And
I'm impressed myself.
The way you're using the the way you're using the tools is exactly like the way we think. But these little very basics, or not very basic, but like simple but many inspectors that you can concatenate to look
this
into
is really
things.
nice. I mean, one thing I've never really done, I know can be done, and I will have to look at some point, is how to do inspectors that actually have entry forms and where you can type something in. It's not just inspecting, but even doing user interface. I've seen others do it, so I know it can be done. For example, in my rules, let's take any rule. Doesn't matter which one. Any rule. So this is just a simplification rule for Boolean algebra. So now, of course, I would like to have a thing like a bit like in the SMAC parser views, where you can type a term and get it rewritten immediately. And of course, with completion support for helping to type terms, because it's very restricted, right? In this context, I can't really type many terms, so it should be very helpful to have completion in there. So this is for future projects. And actually, one thing that since I started using Pharo and MGT, I think the main change it made in my habits of using computers is the importance of good user interfaces. I was, like most computational scientists, I basically get perfectly used to bad user interfaces, and this is the state of the art, and it can't be better. They have to live with that. Life is tough, and you have to learn Unix command lines and terminals and scrolling and all this stuff. You have to do that, and now, of course, I'm less and less inclined to accept this world, which is maybe, I don't know if it's good or bad, but it's certainly the most important change of attitude since then. So now I want, even for myself, I want these things to be convenient, not just for others. So it's always more work. But it's a nicer world. I mean, I show this to people also with this perspective, saying, look, don't look at this and say this is strange. Look at it and say, do you want to work like this? Suppose it were something that you learned at school. Isn't it something that you want to? And most, yeah, of course, I want to work like this. But of course, I also want to work with my familiar tools, and that's for the moment, that's a bit of a conflict that remains to be solved. So
sure, but it's still, this is very, very impressive work. It's really, really cool. I'm very keen to see how this one evolves. Definitely.
Oh yeah, it will. There's so much to do. My to-do list is so long, so I stopped writing it down. So it's too depressive, so I just go on. That's also something I like in the general, say, the small talk way of doing things, that you just you don't have a big design goal. You say, oh, I think I need this, and you discover the tools you need as you need them, and then you do them. It's not you don't start out and do a toolkit and implement it and then find out that half of the functions don't make any sense. So the idea of really developing tools in parallel with the stuff you want to do, I think this is great. It's not something I want to give up again.
Okay. Well,
now, of course, I know I've made myself 100% dependent on what you do on Glamorous Toolkit, so please don't stop.
Okay, we will try not to.
It's my most serious dependency at the moment.
I see. Yes, and yeah, on the one hand, guys, like people talk about, like open source, and then you do open source, and so then you're not dependent on anything. But
no, it's not true.
But then there are these other ways of depending, which, because I know ideally, if people sometimes ask, so what is the goal with GT, is that we would like people to copy us, right?
Yes,
because that's the only thing in which this one will work at scale. But ideally we want people to copy everything, not just little bits and pieces, right? So because like, for example, this thing that you've built here, right? You have you have a language, you have the tools to help you build the language and debug the implementation of the language. You have the tools to inspect and debug the results of executing the language in a certain program, and you have the tools to edit the language in this literate programming or literate mathematics, or whatever the name is. way, right? And it's all together in a platform that doesn't assume anything
Right.
from what you needed, right? And it's not a trivial problem. It's actually reasonably complicated. And but until people will be copying this, it's still a lock-in, basically.
Yes, of
right?
course.
Because there's no, like, it's hard to find all of these together in some other place, right? Which is it's not our intent, but it is. And I was just saying that there's this I understand very well what you mean by that, basically hard dependency. And
yeah, I agree. As I say, I'm a researcher in academia. I can afford to waste my time on things. So in a way, the risk for me personally is not that important, and I can afford to do it. And my main goal was to say, well, I have to explore this. I want to know if this is the way I want to work, and the answer is yes. And the only way to get to that answer is to actually try it, right?
Yeah. And it's really impressive.
In a way, this is a research project on how do I want to do scientific computing, and I found my answer. I mean, of course, I know your system is not designed for scientific computing specifically, or even remotely. It does a pretty good job at that, nevertheless, and I can certainly see many things which I would have to add to make it the scientific computing platforms. But I also say I could actually add all of them. I mean, I don't have the time to do it on my own, but there's nothing that blocks me from doing that. So if I ever can convince some funding agency to give me enough money, I know it could be done. So it's which is reassuring in a way. And yeah, I agree with you. You really want many platforms like that. I mean, you definitely want. I want Glamorous Toolkit for Android, for example. Although I wouldn't want to do the same things on there, but I want the same kind of environment. And I certainly want a version adapted to supercomputers, and they have other constraints. So the current implementation would probably not be very useful on a supercomputing cluster as the ones I have because of their restrictions. But one could implement the same idea on those systems as well, and it would really be nice if there were lots of them. Yeah. I agree. You want people to copy the idea. So yeah, definitely.
Yes. Now about the like this idea with the supercomputer. So right now you're using GT as the UI, as the knowledge management platform, and as a computation engine, right? And they're all in one because it's very convenient. It's Smalltalk, and you just put everything in an image. But that's why, right? In the target with Glamorous Toolkit is not to be an execution necessarily. Is not to be the execution engine. Because we think that systems are always heterogeneous, pretty much.
Yes,
and they're always in some other language. So which means that GT is primarily targeted to being the front end in which you're composing the views to work with something. And this is why, so when we're saying about this, when I was mentioning the distributed Smalltalk, in fact, that one is also just a subcase. So we have the same proxy model to work with the Smalltalk, remote Smalltalk image that we are using to work with the remote JavaScript or remote Python execution. So the proxy model is literally the same.
I actually have my own project in that space as well, which is this one. The underlying model execution engine is not Python, but is Geeks, which is a package manager, container manager for Linux. So you can think of this as a way to compose on the fly something like a Docker container and run it on a different machine. Well, for now it's on the same machine, but what my code does, well, this is just the list of packages I have in at the moment, and then I have some tools to compose environments from these packages, and I can save them, send them to a different machine, and run them. So this is what you're running there is good old, basically Unix processes. All the software package in here is just you find things like GCC and Emacs but also scientific simulation code and so on. So this is my version of this, another side project. So that is again exactly this perspective of GT being my workbench, where I
Yes.
compose my computation and then say, push a button and say, compute this somewhere else and get me the results. And then I want to view it on my screen, and all the computation happens elsewhere. Yeah.
Yes. So one of the things that maybe I think that's one part of it, and then but then there's still the link for the so the link between the two worlds, right? So the question is, what do you want to get back?
Yes.
So right now, right, for example, with this one, I assume that there's a lot of strings going back and forth.
Yeah, it's nothing but strings, of course. Unix don't know. Yeah.
Yes. So in the case of Python or JavaScript, there we literally work with a proxy. There is a full proxy model inside GT that can work with the remote Python object or the remote JavaScript object. And we're using the proxy model is reasonably generic. We're right now exercising it in 4 different things. So we have JavaScript, Python, there's remote GT, and there's also a gemstone, which is this is a larger database that can work on multiple processors. And so there's another piece that is reasonably generic, and then can be used for other types of runtimes, basically. And then you also have the debugging part. So in the case
definitely.
in the case of JavaScript and Python, we can get the debugger, and it's integrated into the default GT debugger, right? But then you have a debugger over the other runtime, and that's also we've exercised those just to be able to say, yeah, we kind of reached the reasonable generality that that probably can be useful for unforeseen types of situations. So takes those into account when just planning your next steps.
Yeah. But I mean, I've been looking at the Python stuff, the Python bridge and the stuff for a while, and it's actually part of what I want. The big problem I have with it is that it has a single Python environment for your Glamorous Toolkit installation, and I need, whatever I do, I need 5 different Python environments. So this is simply not flexible enough for my purpose. I know I've looked at it in enough detail to see that this is not very profound. It just needs some superficial reworking. But and this is again one of my goals here. I want to use Geeks to compose my Python environments, because it's the only way to compose an environment which doesn't only package Python, but also the C dependencies inside the Python. And in scientific computing cases, that's where most of the action actually happens. So the idea is, I have a thing here called GX Python environment. What do you call this? I know there's a GX environment, and it should be a subclass. Oh, I didn't load the latest version in here. No, it's the problem with it. Something I do and I should not do is have several GT images in parallel. So I need to pull the latest stuff over here. And then I should have a GX Python environment, and that's the idea. So I have a Python, and my goal is to plug this into Python Bridge at some point. Again, I have too many things to do. It doesn't advance at the speed I want, but that's the idea, that I can combine all these things, because there's so much scientific code which can be, say, remote controlled from Python, that this is really an entry point. And as you say, with access to debugging and all this kind of stuff. And there's the Python environment, because I've added this quite recently, and now I have it, the GX Python environment. So this can run a script, and then ultimately I want to be able to use these environments in Python Bridge on a remote Python job, and write remote control from GT with the debugger and all this kind of stuff. I'm pretty sure that all this can be done. I don't see any fundamental obstacle except that it needs to be done and to find the time to do it. But
super cool.
That would actually be the point where I could reasonably well sell GT to people in scientific computing. If you can tell them, well, you can run your Python code and do something useful with that. I think that's the point where people will start to bite, I think.
Okay. Sounds like a plan.
Sounds like a plan, for taking over the world.
And on that note, thanks a lot for for this tour. This is absolutely impressive. And
well, thanks for the platform, which is absolutely impressive.
okay, thanks a lot. See you around.
So I'll keep you informed about future developments. You will see them on the Discord. Okay. Well, thanks for the conversation. It was nice to have your feedback on this.
Bye.
We'll see you later. Bye bye.